we present SORNet, Spatial Object-Centric Representations for Sequential Manipulation. In sequential manipulation tasks, a robot needs to constantly reason about the spatial relationships among different entities in the scene and plan its actions accordingly. In the example shown here, the sugar box blocks closure of the drawer, so the robot should remove the sugar box before closing the drawer. Traditionally, the spatial relationships are inferred on top of explicit estimated states, such as 60 object poses, that are then fed into a task and motion planning pipeline to generate actions. However, it is non-trivial to make explicit state estimation methods work reliably on unknown objects or when objects are in close contact, which is common in manipulation scenarios. An alternative approach is to train a neural network that generates visual motor policies directly from RGB images. However, these end-to-end approaches do not explicitly reason about spatial relationships. As a result, the long horizon and constantly changing environment in sequential manipulation make these end-to-end policies hard to generalize. We present SORNet, or Spatial Object-Centric Representation Network, that enables spatial reasoning without explicitly estimating the object states. The key idea of SORNet is to learn object-centric embeddings from raw RGB observations that capture spatial relationships among the objects and the environment. We demonstrate that the learned embedding can be applied to scenes with unseen objects in a zero-shot fashion for predicting spatial relationships, classifying skill preconditions, and regressing relative direction between entities. Our work is inspired by prior work on learning to classify preconditions for primitive skills. Compared to these works, SORNet is more general in the sense that it works with an arbitrary set of objects without retraining. Our work is also closely related to neurosymbolic approaches for visual reasoning. But unlike these works, SORNet does not perform explicit object detection or segmentation, and it generalizes better to unseen object instances without any fine-tuning. Here, we highlight a couple of key properties of SORNet. First, the supervisory signal that SORNet receives during training is purely logical. However, the learned embedding can be used to infer continuous quantities, such as which direction the end effector should move to approach a certain object. Second, SORNet does not require any retraining or fine-tuning when applied to novel objects. Here, we show a subset of the different objects from the training and testing split of the Clever Cogent dataset. Trained only with objects from condition A, SORNet is able to figure out spatial relationships among the objects from condition B with no fine-tuning. Let's now take a look at how SORNet works. The input to the network is an RGB frame and a set of image patches, which we call canonical object views. Note that the canonical object views serve as queries to the network. They can be any image of any object, which need not to match with the object in the input frame. In addition, during inference, only a single image per object is needed to perform any prediction related to that object. SORNet first split the input frame into context patches and concatenate them into the canonical object views. Next, the sequence of images patches is linearly projected and flattened into a sequence of vectors. Then, this vector sequence is added with positional embedding and passed through a multi-layer, multi-head transformer network. The tokens from the final layer of the transformer corresponding to the canonical object views are the object embeddings. Once the object embeddings are obtained, they are used to predict logical statements about the objects and the environment using the predicate classifier. The predicate classifier consists of a set of two-layer, multi-layer perceptrons, each corresponding to a type of relationship. The unary MLPs predict statements involving only a single object, such as whether the object is on the left side of the table. The binary MLPs predict statements involving a pair of objects, such as whether object A is stacked on top of object B. The unary MLPs take object embeddings directly, whereas the binary MLPs take concatenations of two object embeddings. Note that the design of our network enables generalization to an arbitrary number of query objects without retraining. As shown here, the number of outputs can change adaptively with the number of query objects. We first evaluate our model on predicting spatial relationships between objects on Clever Cogent. The Clever Cogent datasets consists of images containing up to 10 objects. Each image is labeled with 4 types of spatial relationships: left, right, front, and behind. The dataset is split into 2 conditions. The model are trained on condition A and tested on condition B. Note that unlike most prior works, SORNet does 0 fine-tuning on examples from condition B. We can see that SORNet achieves significantly smaller generalization gap than MData, a recent work which also reports zero-shot result on Clever Cogent. Here are a few qualitative results. Next, we demonstrate how to use SORNet in real-world manipulation of novel objects. Here, the SORNet model is trained on predicting logical predicates in a simulated tabletop manipulation dataset. The model is applied to real-world observations containing unseen objects without any fine-tuning. A symbolic planner generates a sequence of operators based on the predicted predicates, which is then executed by the robot. Here is our experiment setup in real world, which contains 4 colored blocks that were unseen during training, a Franca Panda robot arm, and a table that is divided into 4 overlapping regions. Taking an input frame and a set of canonical object views as queries, SORNet generates a list of logical predicates. The symbolic planner generates a plan according to the predicted predicates and a set of goal conditions. The plan is then executed by the robot in an open loop fashion. Here is another example. Finally, we show how to use SORNet's object-centric embedding for visual server. Here, we train a regressor on top of frozen SORNet embeddings that predicts a 3D unit direction and a scalar distance from the robot's end effector to the center of each object. Then, we use the predicted direction and distance to guide the end effector towards the target object using position control. The arrows here denote the 3D unit vector from the end effector to the object center, scaled by the distance. This experiment shows that although SORNet is never trained on any metric task, the learned embeddings are able to encode continuous spatial relationships between entities. Thank you. Please check out our paper for more details.